Hi, and welcome to our next session here in our chapter on classification. So this is a somewhat longer session. Here I want to introduce basic notation for classification tasks and classification models. I specifically want to discuss the difference between hard label predictions, probabilistic classifiers, and scoring classifiers. I'm going to define what a decision region means for a classifier and what a decision boundary is. And at the end, or at least briefly and roughly introduce two template procedures for mainly constructing probabilistic classifiers, so the generative approach and the discriminant approach. Okay, so we already talked about classification tasks, already told you the major difference to regression, which wasn't very difficult. So we said what's mainly different is how the labels that we observe look like, and that of course we then also in turn want to predict with our model. So we have some discrete output space here, or capital Y, and that consists of a finite amount of G classes. And these G classes, as we discussed before, they can be basically anything, I don't know, red, green, blue, healthy or sick, something like that. They're supposed to be finite. My notation for a number of classes is usually this small g here. And the one thing that makes, I don't know, this notation or whole business of mathematically specifying things now a little bit tedious is that depending on how many classes we have, depending on how exactly we want to predict things, as probabilities or scores or hard labels, notation becomes a little bit tedious and cumbersome, and we have to watch out for that a little bit. So what I want to do here on that slide is I want to discuss encoding of classes at least a little bit. So for the binary case, so if G equals 2, we usually have two convenient choices to encode our classes. So we want to compute with things later on, right? So having things like, I don't know, red or green in there, I don't know, as strings is not so nice for, I don't know, computing predicted outcomes based on numerical data. So usually we're going to encode classes here numerically, either with 0, 1, which is a little bit better for probabilistic models, or with -1 and +1. Usually the +1 class is going to be called the positive class, could be the one that we are more interested in, and the 0 or -1 encoded class is usually being called the negative class. If there's more than two classes, so if you want a multi-class case, then we could use some integer encoding from 1 to G, but very often it's even more convenient to use what we call one-hot encoding. So for every class, we would turn that into a 0, 1 vector, and that 0, 1 vector would be of length G. So if you have 3 classes, we would have 3 entries here in our vector. They would all be 0, 1, and there would exactly be 1, 1 in there, because every component of that vector is associated with exactly one class. So we'd have an ordering of the classes. So maybe we have setosa, versicolor here for a good old friend, the iris data set, and then virginica. So maybe they are associated with these 3 positions here. And if we then have an observation from class setosa, would encode that as 1, 0, 0. But if it would be virginica, it would be encoded as 0, 0, 1. Okay, that's all that is to it. And I guess you can't even see what I wrote there because it's now hidden behind my head. But I guess you can see it on the picture on the left-hand side here. Okay, so let me remove a little bit of the scribbling so we can go on and enable the pen tool again. Okay, I guess it works. So we discussed regression before, and in regression our model F here simply maps also to a real valued output space. Our labels are real numbers, and this is usually also exactly what we want to predict. So there's kind of no, I don't know, not sure whether I want to say mismatch between the two, but there's nothing really we have to, I don't know, take further care of. For classification, the situation is slightly more complicated because sometimes we would like to predict with our model exactly the classes that we have observed. So whether a person is healthy or sick, we want to predict exactly that. But sometimes we also want to model the probability of a person being sick. Or we want to model something like a class score. And the latter two are potentially vectors if we are operating with G classes. The most basic or common form of a classifier when we construct that is usually what we would call a score-based classifier. So we would map from our input space X here to a G-dimensional output space of real values where each entry in that prediction vector here would be a score, something like a preference score for that class. And in order to minimize confusion, this is not necessarily done in all literature, but I'll try to do this here pretty exactly or pretty diligently. Going to distinguish between all of these three cases here also in notation. So I'll use H of X for a model that predicts hard labels, H for hard, pi of X for probabilities or probability vectors, and F of X for scores. Why are we even doing that? Why are we not, I don't know, somewhat content and happy here with hard labeling classifiers? So I guess there's at least a twofold answer to that. So first of all, obviously scores and probabilities are way more informative than hard class predictions. So let's maybe go again to the medical scenario. So contrast the prediction like, okay, I guess you have that specific illness here, you have that specific disease, with an alternative statement like there is a posterior probability of 53% of you having that disease, or there's maybe a 99% probability of you having that disease. I guess the latter is way more informative, and we can, I don't know, we can do a lot more with such models. The other reason is more a numerical one, and that is that from an optimization perspective, it is way easier to work with continuous values in prediction that we can then later on perform empirical risk minimization on, than working with discrete functions that output discrete values. So how do these scoring classifiers then look like exactly? So we have our G classes here, and if we want to construct something like a scoring classifier, we'll actually construct G individual discriminant or scoring functions, Fk, that all map from X to the real numbers. So of course you can also put them simply into a vector, write it like that here. That would give you a mapping to R to the G, okay? And if you then want to turn this into a hard labeling classifier, or you just want to figure out which predicted class you should choose, usually this is done by picking, for a given X, picking the one class with the maximum score. So you just do the argmax on this guy here. And it should also be somewhat obvious that if we only have, or in general, we actually wouldn't really need G of these guys, because there's kind of one degree of freedom that we are using in a certain sense too many here. So it would be okay for G classes to only use G minus 1. And while for the multi-class case, we might actually model G of these functions here, at least in terms of output, not necessarily in terms of numerical optimization on the inside. Specifically for binary cases, we would really just use a single discriminant function, and just use an f of x here, and that f of x would be the score difference between the positive class and the negative class, which we can also interpret as the preference score for the positive class. And in such a case, when we have two classes here and we're using these, working with these score-based systems, where we have scores which go from somewhere, from negative infinity to plus infinity, usually it feels quite natural then to also label our classes, or I should probably say encode our classes with -1 and +1. If you are in the binary case and you want to construct from the score f here for the positive class a hard label, you can simply use the sign function, right? So if it's a positive value, predict a +1, and if it's a negative value, you would predict class -1. And because of exactly these types of operations, this is what I meant with it. It feels quite natural then to encode classes here with -1 and +1. You can also interpret the absolute value of f, and usually the idea is the larger the absolute value of f, the more kind of confidence we have in the prediction. Here's a small example how this would feel like for a 3-class problem. So you can see here for each class the predicted score. So for class 1 we would have a 2.5, for class 2 a -1.8, and for class 3 a 0.7. And the class that's now predicted based on these scores would be class 1, because that has the highest score here. And yeah, you can also see that it's not really obvious now how to interpret the absolute value. I guess we can say they are somewhat close together, but it's not really clear maybe how to turn these numbers here into kind of a probabilistic statement, yeah, in terms of what's the posterior probability now for class 1 based on these score predictions. And this is why we also very much like to construct probabilistic classifiers. So the formalism of the score-based classifier would cover these guys here as well, but for probabilistic classifiers, we are again constructing G functions, one per class. I'm going to call them pi here, pi for probability, pi1 to pi g, but they now should obviously map to the interval 0, 1. And for a given x, actually for any x, if we sum up all of these pi k guys here, the result should be 1, because it's probabilities, right? And one class must occur. Again, the predicted class is the one with the maximal score. Here it's the one with the maximal probability. So this is how we would turn a probabilistic prediction into a hard label. Again, for the binary case, it is usually enough to work with one function here and not pi1 and pi2. And that singular function, pi of x, is supposed to model the predicted probability for the positive class. And of course, in that case, it's then natural to encode our classes with 0 and 1. And of course, there's also the predicted probability of the negative class, which is simply the counter probability, so just 1 minus x. And again, here is a small example with 3 classes, 1 observation. First one has a posterior probability of 30%, second one 20%, last one 50%. So I guess we're going to predict class 3 here, if we don't have any further information or costs or so on the classes. But for seriously imbalanced cases, so where some classes are way smaller than others, or if we would have some cost structure on the errors that we could make for our classes, we might sometimes want to deviate from this standard conversion of scores to classes, or standard conversion of probability to classes. I don't want to talk too much here about that, because that's a whole issue of its own, how to do this algorithmically and properly, but I want to introduce at least the basic concept here that something like that might happen later on. So, and I'm also not going to talk about the multi-class case here, just the binary case. So the idea would be that we want to convert our scores or probabilities to classes, to class outputs, to hard labels by a so-called thresholding operation. So in order to figure out whether our pi of x here is going to be turned into a prediction for a positive class or a negative one, we would compare it with a threshold c, and we can do the same thing for our score here. So standard thresholds would be, we compare our pair of x with 50%, with the 50% threshold. Because if we have a value larger than 50%, well, I guess then the probability for the positive class is the largest one, right? So that's very consistent with the argmax definition we gave on the slide before. And for similar reasons, the standard threshold for a score-based classifier would be 0. So if it's negative, predict class -1. If it's positive, predict class +1. But we can now, if classes are very imbalanced, if you have a certain preference for doing less errors on one class than the other, we might vary that threshold. Here, for example, we have used a score-based classifier and used a higher threshold of 1.1, or here we have used a more liberal threshold for a probabilistic classifier of 40% to predict a positive class. And then we just use that threshold, as I've explained, to turn these scores here into hard labels. That's basically. I just want to make you aware of the fact that sometimes we're going to do that later. Okay, further pieces of terminology: decision regions and decision boundaries. So decision regions are simply sets of points in our input space. Usually denote them by capital X, K, where we predict a label of K. So it's all of the points here in our input space where our hard label classifier, or the derived hard label classifier from our score-based classifier or from our probabilistic classifier, would predict a certain class. So far, so simple. And there's also, and this is sometimes what we're even more interested in, the concept of a decision boundary. So the decision boundary is the region between two classes where we are not exactly sure which class we have in front of us. So this is exactly where the classification, in a certain sense, switches. So I guess the definition is a little bit easier for the binary case. So let's maybe say we have a probabilistic classifier in front of us. Then these points here, they would be exactly in the default case, they would be exactly on the 50% threshold, because this is where we are not sure whether it's the positive or the negative class. Can also write that down for some general threshold here based on a probability or on a score. So for a given threshold, all of the points where we exactly predict that threshold, this would be our decision boundary. And as said before, common case, the default case would be 50% for probabilities and 0 for scores. And for the multi-class case, it's a little bit more, tedious to write down, but the concept itself is very clear. So for a point to be on a decision boundary between two classes, I and J, that would be all of the points where the score would be the same for these two classes, and all of the other scores would be less than the scores for these two classes. Okay? So we are not, because that exactly means we are not sure how to compute the argmax operation, so to speak. Yeah, there are at least two possible answers for the argmax at that point. A couple of further visual examples of decision boundaries. Yeah, so here is how a decision boundary would look like for logistic regression. Here is naive Bayes, something more nonlinear, a support vector machine, and a decision tree. And all of these models we'll study way more in detail later on. We'll also talk about what it means for a decision boundary to be linear, to be nonlinear, where we have these rectangular regions here for trees and so on. So I'll keep it very brief for now here. I want to wrap up with two template approaches for constructing classification models. So one very common approach is the generative approach for probabilistic models. So, okay, what does that mean? What does this generative approach mean? So the idea is to model this thing here. So the class conditional probability. So to come up with a distribution, or to come up with an idea or a functional form of a distribution for all of the observations in a specific class K. So maybe we want to say something like, hey, given that we are in class 1, or given that we are in any class, but given that we are in a specific class K, all of our feature vectors should be normally distributed. Yeah? They should follow the distribution of a multivariate Gaussian, which would be exactly the assumption we would make in linear discriminant analysis, quadratic discriminant analysis, or even for a naive Bayes, with some extra details mixed in, because I guess otherwise it wouldn't be 3 different model classes. If we now make such a distributional assumption, yeah, so if we fix a certain distribution here for the distribution of x, given that we are in class K, what we can then do is we can nicely employ a Bayes theorem to get our hands on this guy here, because that's what we are mainly interested in, right? So we mainly want to reason about, we mainly want to predict the probability of an observation belonging to class K given its feature vector x. So the thing is ordered in the opposite manner than this class conditional distribution here. But what we can nicely now do is we can say, hey, we want to predict this thing here. Yeah. So our probabilistic classifier pi k of x should hopefully be close to the probability of y given k. Should be close to the probability of y being k given our feature vector x. And this we can now write through Bayes' theorem as the conditional probability of x given k times the marginal probability of being in class K divided by the distribution of x. For this here, we can again plug in the law of total probability. And then if you look at this thing here, which gives us a formula to compute this guy, to compute the posterior probability of y being k, the only 2 terms that appear in that formula are the class conditionals and the posteriors. So if we know how to estimate them, if we know how to work with these, we can now construct our model and we can compute predictions, optimal predictions from that. Maybe just a few sentences on these prior probabilities. So that's the probability, or an estimate of the probability of y just belonging to class K as a marginal probability. I guess it should be fairly obvious that these guys here are quite simple to estimate from training data. So just counting frequencies. So below we have an very small data set, maybe from this, I don't know, maybe a subset of the Titanic data set with just an unrealistic number of 5 observations, binary task, whether somebody survived the catastrophe here of the Titanic, labeled with a yes and no. And here for that data set with n equals 5, there would only be 2. I'm not sure where, well, I guess I'm going to call it a positive case, 2 positive cases where 2 persons have survived. So the estimate for pi hat, proportion of the proportion of positive cases in the whole distribution. So our estimator of that would be 2 divided by 5, so 40% in that case. Should also be clear how the decision boundary is defined in such a generative probabilistic model. Actually, it's not defined any differently than in the general case. So if you have now modeled this thing here, or if you have modeled that for any class, you can just compute the posterior probability for being in class K at every point, and the decision boundary is now simply again the set of points where this posterior probability would be for the 2 class Ks 50%. I've already said this type of construction here is followed by linear discriminant analysis, quadratic discriminant analysis, naive Bayes. There's a whole zoo of methods where different distributional assumptions are being made for being in class K, how the features are distributed then, and then the rest just follows the kind of general principle that I've outlined here. And we will study a few of these later on. Maybe be a little bit careful, but it's historically a little bit confusing, is that what I'm calling the generative approach here. So LDA and QDA actually have the D in there for discriminant, and that's a different approach that I want to explain now. So from my terminology, they would be generative models and not discriminant ones. So because what I'm calling a discriminant model is where we do something like empirical risk minimization pretty much directly on our model class. So we have some structure of our model F. I guess the most relevant example we'll study as beginners will be logistic regression. So we directly model what the posterior probability for a class is given a feature vector, and then we put a loss function on top of that, maybe derived from a likelihood principle, and then minimize that for the parameter vector of our model. Examples would be neural networks, logistic regression, support vector machines. So in these cases, you wouldn't really reason about these conditional distributions, but we would directly tackle the prediction problem in a certain sense by specifying a hypothesis space and specifying a loss function and specifying an optimizer, maybe even a regularization principle, and then doing empirical risk minimization. For that reason, you could say that this is a little bit closer to this ERM principle of machine learning, but that kind of is not a statement on whether any of these models or learning algorithms are better than the others. It's just like they're constructed a little bit differently. Okay, that's it until here. See you in the next session.